again today. Now we are going to kind of discuss the mathematician's ideal chain derivation for the ideal chain, freely jointed, Gaussian, all these different methods for this model that we've been working with that's a little bit unrealistic, that ignores essentially, we ignore that bonding component, we ignore bond angles, bond rotations, steric hindrance, any basically molecular details. We just treat it as kind of this ideal random walk, but again, it holds true, and the scaling that we found last time was that RMS end-to-end distance is going to scale as n to the 1/2 L. And this holds for, again, if we're in a theta solvent, if we're in the melt. So there's some real-life scenarios where this expression, we can describe our polymer in this way. So it is useful, even though it's unbelievable that it's still accurate in real situations. Basically, it's telling you chemistry is important. So our lecture 2 was pointless. But anyways, now last time we went through and we derived this from a probabilistic perspective. So it was kind of dealt with a lot of statistical mechanics concepts and these other, and if you're not familiar with a lot of statistics or statistical mechanics, which many of you might not be, this might be a little bit more conceptual way of understanding how you can derive this expression, that RMS scaling, this scaling behavior here, and particularly this variable here. So let's take a look at it from a different perspective. Instead, let's look at the ideal chain model and just imagine it as a set of vectors. So we have n number of vectors with some length L. So we have n vectors with some length L sub I, and you can kind of just treat each of these vectors as the same magnitude, L sub I, but we have some vectors L sub I. So we are going to, again, still uncorrelated. Again, we don't have any reference or any memory from our previous step, so completely uncorrelated. And we're just going to kind of connect these monomers randomly together. So we will vary from L sub I to L sub n. So our R vector here will literally just be the sum of all of your L sub I vectors. So pretty reasonable. I think that makes sense to me. Hopefully it makes sense to you. So on average, again, if these are completely uncorrelated in 1D, what should be, on average, our R vector? Well, it should be 0 again. They're completely uncorrelated. They could either go right or they can go left. So on average, if you have this equal number of steps, if n equals plus n minus, and on average, n plus and n minus are going to be equal on average. If you again, sample over many different runs, many different many different conformations, or sample one chain over time, on average, you'll find that it's because they're uncorrelated, and this is really critical. Because they're uncorrelated, our average value of our end-to-end distance vector is going to be 0. So, but the question is, what will be R squared? What will that be? All right, so we don't have the moment. We can't take the second moment. We don't have distribution here, but we can. If I want to find out what R squared is, I can just take the dot product of those two summations. So I could just take the dot product of my two, basically Li and Lj, and I could sum over all the way from I equals 1 and to j equals n, from I equals 1 to n, from j equals 1 to n, and that's what we'll kind of do here. So let's look, and hopefully everyone remembers their dot product, magnitude. Luckily for us, again, all of our L sub I and L sub j's, they are going to be equal in magnitude. This will always be the case unless you have a very actually, won't be the case if you have a block copolymer necessarily. So, but that's another, just now that I'm thinking about it, polymer, that's an interesting problem. Maybe on an exam. No, I'm just kidding. But we'll talk a lot about block copolymers later on. But, so, if I want to kind of calculate this R squared value, I'm just going to do the dot product, and I'm going to sum everything in this matrix. So you can see that there are, from here to here, I have n rows, and from here to here, I have n rows as well. So let's look back at my, look back at this picture over here. Actually, let me go, let's see if I can go to my presentation. Excuse me that I don't have this already pulled up perfectly, but here we go. Let's say, actually, I'm going to make my own. So I have, this is my L sub 1. So if I do, again, we're dotting, if we look back over here, we are dotting L sub I times Li, Lj for all these. So what is going to be the dot product of L1 dot L2? Well, I know it's going to be L squared, and then what else? What's the cosine of, what's the angle between, oh, sorry, excuse me. L1 dot L1. What is the angle between L1 and L1? Well, they're in the same, they're going in the exact same direction, right? So what is going to be that angle? If they're pointing in the same direction, well, the direction between those things are going to be cosine of, excuse me, it's going to be cosine of, the angle is going to be 0. So cosine of 0 is 1. They're pointing in the same direction. There's no angle between them. So they're going to be the angle pointing in the exact same direction here, or, so actually we're getting a little bit ahead of ourselves. So cosine of 0 is 1, so it's just 1. So that is going to be my L sub 1. What about this one? L2 dot L2. Same thing, right? Magnitude always going to be L squared, and now my angle is, again, 0, 1. So all of these diagonal components here, they're all going to be L squared, L squared, L squared, L squared, L squared, L squared, L squared. Now, the interesting topic, or the interesting point, comes from this L1 dot L2. Now, what are my options for placing L2 in a 1D walk? Well, I could either place it here, or, so this is one possibility for L2 in the plus direction, or I could place it going, I'm going to just show it this way. I'm going to make this, sorry. I'm going to make this blue. This is going to be L2 plus, or I can make it go back and L2 minus. So what's the angle between L1, let's look at this theta. I'm going to change to blue. What is this theta? Well, that's equal to 0 again. So that's fine. So I get my 1. But I have an equal probability. So if this is theta, then my L1 dot L2 plus is equal to L squared. But if I go in the opposite direction, my theta then is what? Well, it's going to be basically minus 1. You could say it's basically minus 180 degrees. Completely opposite direction, right? So that is going to be cosine of minus 180. Let's double check it in Mathematica. And actually, let's confirm it. Actually, one of the good things we could show here is you want to put a degree here. So cosine of 0. What about cosine of minus 180 degree? That's going to be minus 1. Good. But we know how to double check our math. Use Mathematica. Don't think. Anyways, just kidding. So minus 180 degrees. So that is going to lead. So my L1 dot L2 minus is going to be minus L squared. So on average, because these steps are uncorrelated, if I look at all of the next ones, so even if, let's say L1 L squared was a positive, so L squared, L1 dot L3 could be a negative L squared, and so forth and so forth and so forth. So on average, because we are completely either equally probable, it's a completely random stochastic Markov Monte Carlo uncorrelated process, the average value of the cosine of theta ij, where I does not equal j, is going to be 0. So all of those off diagonal components become 0. Now, if I want to sum everything in this matrix, what do I do? So I know I have n rows here. So if I sum all those, everything else is 0. I'm left with L squared. And then how many of those am I going to have? Going down here, I have n rows. So the sum of my matrix becomes, let's go up here. Ta-da! We just obtained the same scaling behavior as our previous method. So we see that r squared half equals n 1/2 L squared. Nice, right? Again, everything's matching with our physical intuition, our theory, our kind of derivations. This is excellent behavior, excellent. And again, I think that this hopefully is a little bit more, I want to say qualitative, or at least you kind of get a better hands-on understanding, especially if you're not familiar with statistical mechanics. So I hope that's helped. We have now our scaling behavior for 2 scenarios. So we have the ideal and contour. And next time we are going to start our discussion. We have our contour scaling. That scales with n. This scales with 1/2. And now we are going to deal with the chemist polymer chain. So now we're going to start to add some molecular details, some chemistry, and see how we can adjust, or how the polymer will change size depending on basically the chemical structure, bond angles, bond rotations, solvent quality as well, basically enthalpic interactions between monomer units and solvents. So we're going to get into some fun stuff coming up here pretty quickly. So yeah, that's it for this video, and I'll talk to you next time. Thanks. Have a good day. Let me know if you have any questions, and stay safe. Bye.